Okay, welcome back everyone. So we're gonna just jump right into this here and let's look at the next example, the next topic here. We're gonna talk about primitive data types in C. And this is an extension off of the knowledge that we just learned in the previous video related to binary numbers. So let's start right there. Let's take a look at just thinking about a variable in particular, thinking of a variable and reflecting on the syntax that we talked about prior, and then we're going to kind of start connecting some topics together and introduce some new things, right? So we saw previously, right, if we've got a variable, we say like int x, and let's say int x equals 5, right? We write some code that does that, and we know, okay, that somewhere in our computer's memory, we're going to store that in binary, okay, and that's actually going to be this number in binary, and that's going to be where we're storing x, right? So a key thing is kind of to reflect on here is that all information, right, stored in our computer system, in our computer memory, is all in binary, right? That has some implications, and we also want to be mindful of the fact that the data type here, that defines the range, right? The range of numbers that we can work with, right? So we know that, for instance, an integer, allows a bunch of negative numbers. For instance, we could have a whole range of negative numbers and positive integers, okay? And one of the things we'll look at, though, is that range, right? An integer range, it's not infinite, okay? It is bounded. That range is bounded, okay? And it has to do with the number of bits that are being used, right? The number of bits that are being used to represent the number, okay? So, data types, anytime we have a variable, we have to define the type. And what we're really doing is we're specifying the range, right? We're specifying the number of bits that we're going to be using to represent that information. And we're also going to be specifying the standard that we're using for how to interpret that binary number. Okay, a little bit more on that later. Okay, let's take it one step at a time. Okay, let's first, on this topic here where we're referring to the range, right? Let's think about, well, what do we mean by the range and what is that? And how can we define it, and how can we define it in a mathematical sense, right? So let's just take an example here. Let's just imagine that we're limited by 3 bits. Okay, we only have 3 bits, right? 3 ones and zeros. Okay, so the smallest number we could represent in that case would be this, okay, in binary. And the largest number we could represent would be this in binary. That's the range, okay? And if we were going to write that as its decimal base 10 equivalent, that range is 0 to 7, okay? 0 to 7. Okay, you can do it out, 1, 1, 1, right? If you do it out, it's 4 plus 2 plus 1, you're going to get 7, right? So, okay, that's with 3 bits. What if we had 4 bits? What would the range be? Okay, and that range is actually going to be this, right? 0 to 15, 4 ones in a row is going to be 15. This extra 1 here is going to represent 2 to the third, or 8, so it's 7 plus 8, we're going to get 15. And so we look at the range in base 10. And let's do this one more time. What we're going to do then is we're going to find a formula based on how many different numbers can we represent. What's the range of numbers we could represent based on the number of bits. Okay, so let's just do one more just to kind of see the pattern. Okay, so for 5 bits, okay, so for 5 bits, that's going to be the range, okay, and this number here is going to represent 2 to the 4th, that last one that we just added, okay, so that's going to be 16, right, so we're going to get 15 plus 16, we're going to have, oops, we are going to have 31 here. Okay, so can we take this, right? If we kind of summarize that in a way, if we summarize this and we look at the number range, what we're seeing is, okay, if we have n equals 3, where n is the number of bits, okay, we know the smallest number, right? The smallest number is 0 consistently throughout, right? 0 throughout. So let's just think of the largest number we could then represent. Okay, so with 3 bits, okay, we were able to represent 7. Okay, with 4 bits, we were able to represent 15, right? With 5 bits, we were able to represent 31, okay? And so effectively, if we want to look at the range, okay, if we want to define something that allows us to look at the range of, the largest number we could represent, we can define that as a formula that's going to be 2 to the n minus 1, okay? 2 to the n minus 1, right? If we plug that in, where n is the number of bits, we could see that holds true, right? Because we would do, like, say, for instance, if we had 3 bits, we're going to say, 2 cubed minus 1, 8 minus 1, 7, right? And so on. You can see that it's going to hold true throughout, okay? So this is defining, right? We can see as the number of bits grows, right? We're able to store larger and larger numbers. Okay, why am I bringing this up, right? Is this has to do with when we look at different data types. There's a whole lot of different data types we can use. We're going to have some that are very common. But let's just take an example here. If we look at, say, defining a integer. Okay, if we have an integer and it's represented as having 32 bits, okay, what we're going to see here is this gives us a range of numbers, okay, and we're losing half of the space, right, half of the range, because we're also going to allow negative numbers. And I'm not going to get into how negative numbers are encoded in binary. That's a topic for another course. We don't want to waste our time with that now. We want to focus on getting into the programming logic. But effectively what we're doing, right, is if we had started our range at 0 and we went to, say, like something around the 4.2 billion roughly, right? When we're storing negative numbers, right, we just kind of cut that, we just shifted that range over where we have 0 in the middle, right, and we're going to go negative 2.1 billion, right, to positive 2.1 billion, right? So we just kind of shifted that range over. But you can see the number of bits, right, defines the range that we have to work with, right? So if we went down to 16 bits, right, we're going to have a much smaller range here. Okay, and if we used 1 byte, right, 1 byte equals 8 bits, right, we're only going to have 256 possible combinations here. Okay, so that's so the number of bits matters, right? That gives us how much we have to work with, right, with the range we have to work with, and it's not infinite. Okay, so we've got these different data types available. Okay, and before I move on, right, I just also want to kind of reiterate one thing, because it has to do related to this topic of working with binary numbers, is the fact that, remember, right, if we kind of go back to this previous slide here, when you declare, I mean, this is a key topic, right? This is a key thing that I see students commonly making a mistake with. When you declare a variable, right, it's really important that you're initializing it. Okay, like here we're initializing it to 5. Okay, because if you don't, right, there is some existing thing in memory here that is some other binary number if you do not initialize it. Okay, and then you could be using some junk data. So just kind of keep that in mind. We've mentioned it previously, but I really want to kind of emphasize that point because it's a common mistake is not initializing information. Okay, all right. Now, I had showed this. I originally, when we talked about the range of numbers, I put the smallest range as 0, and then we looked at how we could shift it over to represent negative numbers too, like half the range to represent negative. If you want to force force the range, the smallest number of the range to be 0, and then maximize the largest potential number, you can use this term here called unsigned. Okay, what that would do, right, is we take a look at these 32 bits, and now we're taking that entire range, okay, and we're going from 0 all the way up to 4.2 billion or 4.3 billion, right, roughly. Okay, and again, that number is represented. We know that largest number here because we're saying that's going to be 2, right? We're using 32 bits minus 1. If you plug that in, right, you're going to get that largest number there. All right, that 4.29 billion. Okay, so the unsigned is a way to do that. It's allowing you to force that you're only going to have positive numbers. Right? If we want to have really, really long numbers, we could use this here. We can continue every time we use the word long one more time. We're going to add 32 bits. So you can get really, really large numbers if you really needed it, which would be pretty rare, especially in a class like this, an intro class, for us to do that, but we're going to still see it. Okay. So we have these things, right? These are what we've been looking at in these this diagram here. These are primitive numeric data types. Okay, when I say I use the word primitive, I'm using the sense of that we're going to see later on that there's when something's not primitive. I use the word primitive meaning that they are built into the language. They're built into the C language. Okay, they're basic building blocks that we can use to build other things. Okay, so primitive it's a common term for describing these things. It means basic. It means built in, and we can see how we can kind of take these different basic primitive data types and build much more complex things later on. But that's a topic for another day. Okay, let's look at another data type here referred to as a character, and we declare this using just the word char, short for character. C-H-A-R, char means character. Well, what is a character? Okay, so character it's not a number, it's a single character, right? A single character. So examples of things that would be in that range, okay, would be, we could have numbers like 0, we could have, numbers. We could also have, right, letters would be an example, okay, capital or lowercase, right, even punctuation, all right? These would all be examples of characters, okay? To represent a character, notice I use this single quote. Okay, notice I use these single quotes around a character. Okay, that indicates that that data type that we're using, okay, is a character. So when I'm initializing it, see here when we're initializing, right, we've got here that we're actually initializing the character data types for arrow body and arrow head. Okay, the single quotes indicate that we are referring to a character data type. Okay, that distinguishes, there is a difference, and this is a subtle difference, right? This, right, as a number is not equal to this as a character. Okay, has to do with data types. 0 as a number is not the same as 0 as a character, right? Where it could because the ranges of how we're storing these things is different, right? As a number, we can have, 583, right? Whereas a character, we cannot do that. It's just how we're going to operate and store this information. You'll get a better sense of this later on, okay? But effectively, it has to do with, how it's being stored and how we can operate on it. For instance, if it's a number, kind of adding something to it makes sense, right? But a character, it could be like, what is taking a exclamation point and adding something to it, right? It can mean something completely different, or it can be nonsensical. All right, don't get carried away with that. So here's just an example of declaring initializing in characters, okay? And I'm not going to get too carried away with this. We'll come back to how we can print them out and read in characters from the user. I really want to mostly emphasize this point here, okay? And this has to do with how characters are stored in your computer system. Okay, and we're using something called the ASCII standard. It's been around for decades. Okay, the ASCII standard is a way of which we're taking a binary number. Okay, for instance, take example this binary number here. Okay, which would convert to 32 in base 10, and that indicates a space character. Okay, so that indicates a space character, which would be a single quote, space, another single quote. Okay, this binary number here, 97, okay, represents A. Okay, and this has to do with, again, everything stored in your computer system, right? Everything in your computer system is being stored as ones and zeros, binary numbers, okay? And if we're using in our program, right, if we're declaring something as a character, right, we're interpreting it, we're going to take that number that it's there, right, say 97, and we're not going to interpret it as 97, we're going to actually interpret it as this, okay, even though in your computer it's actually represented with ones and zeros. Okay, so let's get a sense of how this works, and this might make it kind of sink in a little bit because we're going to do some things that might look a little weird when you haven't seen this before. Here's a character, right? I'm looking at a simple little program here. I've got a character, and I'm declaring a variable of type character called my char, and I'm initializing it to the character A. Okay, and what I'm actually doing here is something that's a little weird to do, and I'm showing it because it's kind of get at this point of the different data types and what they mean. Okay, is what I'm doing is I'm setting this character actually to an integer. Well, that's weird, right? What is A as a character? What does that mean in terms of as an integer? And then I'm printing it out to the screen. I'm saying print that integer to the screen. Okay. By the way, right, I can also print, if you want to see both, I could also print the character to the screen, right? The details on how to do that are not that relevant right now. I'm using something called a format specifier that we'll see later on. %C means printed as a character. We'll talk more about that later on. So effectively what I'm doing is I'm printing the character and I'm printing the integer. Okay, but look at how we're initializing the integer. Okay. We're initializing it based on, like, what does it mean to take something as character A and interpret it as a number, as an integer. So I'm going to run this. Okay, and if we look down here, notice that I say my character equals A. That makes sense. But we said my integer equals 97. Right? Well, how does that 97 come about? That seems really, really weird. Okay? And that has to do with what we were looking at previously here. We're saying that A is stored in binary as 97. Okay? So you can see how we're still storing everything as binary. It's just how we're interpreting things. Okay? The range matters, right? What do we want? What is the range of numbers, okay, that we're storing? Okay, what do we want to be storing? Are we trying to store characters? Are we trying to store, integers? If the integers are always going to be positive, we can use that unsigned to make sure that it's always interpreted that way. Okay. Last thing I'm going to show you in this video is I want to look at something called these escape sequences and these kind of special characters. Okay, if I use backslash for characters, I'm referring to something, a special character. Okay, so we've already been using one. We've been using new line. /n means something different than n by itself, right? We were doing that. It means a new line, right? We already looked at that. We did that here, for example. Say new line so that we print on a new line. Okay. This is a single character, right? Now we actually write it as /n, but the computer treats it and stores it as a single character, meaning a new line. Okay, new line character. There's other characters we can use, right? So say I wanted to print something as a quote. if I wrote, he said something important, all right, that's the quote, right? If I run this right now, the quotes are not going to show up, right? He said something important, right? Doesn't show up. If I do /quote, /quote, those quotes will be displayed. Okay. The reason we have to use / is quotes mean something else in the context of the C programming language, right? So here we see the quotes show up, right? But in the C programming language syntax, quotes mean something different. Okay, it means text or a string of characters. So the / means something different. It means that we treat it as the character quote. Okay, there's a whole bunch of them. We could do it for, I won't list them all out here, but I'll just show you a few, right? We could do it for tabs, single quotes, even if you want to print /, because / means something different. 2 backslashes, right, represents the / character, right? So this is, the / is used as an escape character, right, to allow us to do these different types of important characters that we don't really have an easy way of typing and writing into the language. Okay. All right, now we'll practice these things, right? I know it's kind of tough going through these the first time you hear it, right? It's a bit confusing. The only way to make this stuff stick is to apply it, right? We got to solve some problems. We got to build some stuff using this. And I would like to emphasize, right, is when you're first seeing some of this stuff, the topic might seem a little bit dry, but I think programming gets a lot more interesting once you actually start building things and solving real problems. But it gets hard to jump into that until we've kind of got a little bit of a foundation to work on, so that we understand what we're doing when we're building things and have that kind of strong foundation. So we'll get there. It's just going to take a little bit of time. All right, so we'll continue on. We're going to kind of continue on with the topic of data types and some of the subsequent videos here, and then we'll kind of get to some of the more interesting stuff later on where we can kind of use some of this logic to build things and get some cool stuff working. All right, so take care and thanks for watching.